Hi, my name is Kwame Anderson, and these are my results for my project on brain tumor diagnosis. In this presentation, I'll be talking about the background of the project, the technical problem that the project is based upon, the machine learning algorithms that I used, a little bit about the data set, the experiments that I conducted, and the results of those experiments. Now, one might ask, why is this field so important? On a yearly basis, about 350,000 brain tumor cases are diagnosed on a global scale. Early diagnosis and treatment are necessary in order to ensure a high survival rate in patients. It's possible that doctors may miss subtleties or misinterpret data that they're looking at, and this is where AI kind of comes in handy. This leads to the framework of the problem that I'm addressing with this project. Throughout my work, I used thousands of MRIs to train various machine learning classifiers, making this a supervised learning task where the models were designed to classify brain tumor types. Now, here is what my work covered. Given unprocessed MRIs, determine if the tumors are present and if so, classify the type of tumor. Before we talk about the models and experiments, I'll discuss the data that I used. The data contained 7,000 MRIs that consisted of various sizes and included three different types of tumors, which are the pituitary, the meningioma, and the glioma tumors. These tumors all required pre-processing, which involved resizing the images using cubic interpolation to maintain the aspect ratio, as well as applying a color threshold in order to remove background noise from the images. With the data covered, I'll talk about the experiments that I conducted. These experiments were using three different machine learning classifiers, which were k-nearest neighbors, support vector machines, and convolutional neural networks. Another experiment that I wanted to try was the specialized models, which I'll talk about here shortly. The last one was the tuning of the hyperparameters for these machine learning classifiers in order to improve the accuracy of the models. I'll start with my first and most anticipated theory. This was the specialized models. The specialized models, what they are is training a specialized set of machine learning classifiers on a subset of the original problem. So in this case, instead of using a multi-class classification framework for the problem, turning it into a binary classification problem. What I started with was using each of the tumor types as a label that the SVM and what I'll show later, the k-nearest network or neighbor, for determining the tumor type. As you can see, we get about an 86% accuracy for the unspecialized model. When training it for the specialized model, we can see that the labels that it now uses, and this one is off of a SVM that was trained on the pituitary model or label, it'll either predict other or pituitary, and that raises the average accuracy for all the labels to 93%, or about a 7% increase. The same was done for k nearest neighbors, where we see about an 85% accuracy before specializing the labels, and then a 92% accuracy for the average of all of those labels when using the specialized models. From here, I concluded that the use of specialized models does in fact impact the performance of the machine learning models, and that using it in this specific case is very beneficial and better over using the original trained models. Next, I want to cover the fine-tuning parameters for SVM and the k-nearest neighbors. So for this, I use grid search and played with the parameters for the C values to determine if that accuracy would change any higher, using the previous claim that specialized models work better than the standard models. And that accuracy is displayed here. And I have the same thing here for k nearest neighbors. And using the accuracies shown here, I've established that the parameters do have some sort of effect for the accuracy of the model, although this could just be, for this specific instance, generalization for k nearest neighbors and SVMs given the complexity of the data that we're working with. The last experiment that I wanted to do was the usage of convolutional neural networks. Unfortunately, I wasn't able to get this model to work due to struggling with the loss function that I used, which in this case was binary cross entropy, and I had a lot of exploding gradients. The CNNs I want to talk about because they're able to learn from feature extraction from imaging data and various other applications, unlike the k nearest neighbors and the support vector machines. I expect that this machine learning algorithm would perform the best, and we'll continue working with it to achieve conclusive results going forward. But with that, I'll end the presentation here. Thank you for listening to my study on AI brain tumor detection, and I hope you have a good day.